Good afternoon, guys. It's Mr. Kilburn. I'm sure the play went really well last night for those of you who are in it, and I'm hoping to get there tomorrow night, maybe tonight. We'll see how it goes, but you guys are amazing, and it's really just, it's always cool to see students up on stage, just stepping out, maybe out of the comfort zone and doing well, so you guys are rocking it. Okay, so question 34. It's definitely challenging, but it's still one I want you to work through, but I'm going to get you started. Okay. So as you are, moderately familiar with now, when you're doing an optimization problem, you need a couple different equations, a primary and a secondary. So this image is not in your question in your textbook, but I just snagged it online just so you had a visual for what an industrial tank that's cylindrical with hemispherical ends might look like, something like that. Okay, it's not perfectly hemispherical, but you get the idea. All right, so two equations. So first our primary equation, and that's going to be the volume. So the volume of a sphere, which would be the two hemispherical ends put together, 4/3 pi r cubed, and the volume of the cylindrical part, pi r squared h, and all of that equals 4,000 cubic feet. Okay, the secondary equation has to do with the surface area. All right. Now, the surface area formula for a cylinder is 2 pi r squared plus 2 pi r h, but we don't have the two areas for the bases because those are hemispherical. So it's just going to be 2 pi r h for the cylindrical piece without the ends, and the formula for the surface area of a sphere is 4 pi r squared. Again, the two hemispherical ends put together. All right, and that's going to be equal to the surface area. So as you're, also somewhat familiar with, we need to take one of the equations, solve for a variable, plug into the other, set equal to 0, derivative, all that good stuff. All right, but there's a little bit of a twist to this one, and it comes in right here, where it says the hemispherical ends cost twice as much per square foot of the surface area as the sides, meaning the cylindrical piece. Okay, so we need to deal with that. So I'm going to get you set up, get you started, and then let you take over from there. Okay, so first of all, notice in our secondary equation, there's no constant equal to a constant. And normally that's the primary equation, the one set equal to a constant, is the one that we're going to solve for a variable and substitute back in. So the variable we're going to solve for in that primary equation is the height. So starting over here, I'll just start writing it. So 4/3 pi r cubed plus pi r squared h equals 4,000. Subtract 4/3 pi r cubed to both sides. And we now have pi r squared h equals 4,000 minus 4/3 pi r cubed. Divide everything by pi r squared. All right, all that cancels. Change color here to show that. That cancels. And I have h equals 4,000 over pi r squared minus, well, what's cool here is the pi's cancel, that r squared cancels, and leaves just one r up top. So after all that, we're left with 4/3 r. Okay, that's what h is equal to. Now I'm going to leave that be for a second and deal with this aspect of the cost, that little twist they gave us. Well, we don't know what the unit cost is per se, if it's $10 or $12 or whatever per square foot. So it doesn't really matter. So we're just going to call the cost K, okay? The unit cost. So let K equal the cost, unit cost per square foot. Okay, well, the total cost, all right, is going to be double for the hemispherical ends, pi r squared, okay, and just regular, whatever that unit cost is, for the cylindrical piece. Okay, so I'm going to just distribute that 2 here and factor out a k. Okay, which would take me to the cost being 8 pi r squared plus 2 pi rh. Again, all I did was distribute the 2 and factor out the k, the unit price, unit cost. Okay, so at this point, I'll take you one more step. Let's get this in terms of just r, all right? So that k can stay outside. And I have 8 pi r squared plus 2 pi r. And again, we figured h to be 4,000 over pi r squared minus 4/3 r. Okay, so I'm gonna let you take over from here. All right. Now you're going to want to distribute that 2 pi r, take the derivative to both sides. Okay, so once you start taking the derivative, you're going to have dc to dr, and go from there. Take the derivative, set it equal to 0. Once you get r, all right, plug it into the second derivative and determine if it's concave up or concave down. Remember, you just want to know if it's positive or negative. All right, so if it's negative, what will that tell you? Or if it's is it a max or a min? All right, and plugging into the second derivative with a critical point will do that for you. The second derivative is actually pretty short and sweet. It's not that bad. Okay. All right, so I'm going to leave you there. Do your best. Obviously, work together. You guys are having a great year. Appreciate it. And I will see you on Monday. Take care, guys. Bye-bye.